Hello friends, this is a video about an overview of Hadoop framework. Let's go briefly about it. Nowadays in a software company they are facing a big challenges because of the storage of data. In research today is to provide mechanism for storage, manipulation and information retrieval on large amounts of data. For example, let's take Facebook, which initially used relational database management system to store its data. Due to the increasingly large volume of information generated on a daily basis, like from a 15 TB dataset in 2000 to a 700 TB dataset in 2010, one of the Facebook's largest cluster holds more than 100 PB of data, processing more than 6,000 queries a day. Now let's talk briefly about big data. What is big data? Big data is used to refer to a collection of large data sets that may not be processed using traditional database management tools. The term often refers simply to the use of predictive analytics or other certain advanced method to extract value from data and not refer to a particular size of datasets. Some of the challenges involved when dealing with big data goes beyond processing, starting by storage and later analysis. Plausible solution is to make use of parallel and distributed computing. Such processing is accomplished using clusters and grids, which use generally commodity hardware to aggregate computational capacity at a relatively low cost. Although parallel and distributed computing may be one of the most promising solutions to store and manipulate big data, data dependency and integrity, cluster load balancing, and task scheduling are major concerns when dealing with parallel and distributed computing. Adding the possibility of an almost certain machine failure, the use of these concepts becomes non trivial to inexperienced programmers. Several frameworks have been realized to abstract these characteristics and provide high level solutions to end users. Now let's talk briefly about Hadoop. Hadoop, how it is introduced. An employee of Yahoo at the time and a professor named Mike Cafrilla, who is working in University of Michigan, developed Hadoop, later called the Apache Hadoop framework. It is an open source implementation of Google's MapReduce approach. It uses the same idea from Google's, hiding complexity from users, allowing them to focus on programming. The Apache Hadoop framework is written in Java, provides solutions to store, manipulate, and extract information from big data in several ways. The framework has evolved over the last few years and promotes data integrity, replication, scalability, and failure recovery in a transparent and easy to use way. All these factors have made Apache Hadoop very popular both in academia and in industry. The early adoption of Hadoop by the research community has provided rapid evolution and development of new features to the framework. Over the last 5 years, the framework received numerous contributions from researchers, most of them published worldwide in journals and conferences. The large number of publications makes it difficult for researchers to find specific topics or areas that still need further investigation, resulting in a need for an unbiased analysis of the scientific and technological research results obtained in this field in the past years. There are two basic components of Hadoop, MapReduce and HDFS, which is known to be Hadoop Distributed File System. What is MapReduce? A MapReduce program consists of two types of transformations that can be applied to data any number of times. A map transformation and a reduce transformation. A MapReduce job is an executing MapReduce program that is divided into map tasks that run in parallel with each other and reduce tasks. The MapReduce programming, now highly used in context of big data, is not new. One of the first uses of this was on the Lisp programming language. It relies basically on two functions, map and reduce. The great novelty here is that the approach hides from users a lot of complexity of parallelization and distribution. Users can focus on the functionality of their programs and the framework abstracts the complexity and controls the infrastructure. Now, what is HDFS? At first, we will know about the Hadoop cluster. Hadoop cluster is a collection of racks. Racks are the collection of nodes. Hadoop uses blocks to store a file or parts of a file. Now, what are the objectives of Hadoop? Parallel and distributed computing currently has a fundamental role in the data processing and information extraction of large datasets. Over the last few years, commodity hardware became part of clusters. Since x86 platform cope with the need of having an overall better cost performance ratio while decreasing maintenance cost. Apache Hadoop is a framework developed to take advantage of this approach. Using such commodity clusters for storage, processing, and manipulation of large amounts of data. The framework was designed over the MapReduce and uses the Hadoop distributed file system as a storage file system. Hadoop presents key characteristics when performing parallel and distributed computing, such as data integrity, availability, scalability, exception handling, and failure recovery. Even more, these features are presented in a transparent manner to the user, which represents a novel approach to newcomers. Now, let's talk about the contributions which are made on Apache Hadoop. So, these are the 9 contributions which are made on Hadoop till date. Now, let's briefly talk about one by one. So, scheduling. Scheduling alongside with storage is one of the most critical aspects of highly concurrent parallel system and was a topic addressed by a large number of the studies. Originally, Hadoop comes with 3 schedulers: FIFO, FAIR, and capacity. The default Hadoop scheduler is the FIFO, where jobs are loaded into queue and scheduled to execute according to their order in the queue. The FAIR scheduler was originally developed by Facebook and later released to Hadoop community. It gives a fair share of the cluster capacity over time and so its name. Jobs are put into allocated pools, which receive a guaranteed minimum number of map and reduced slots. Using preemption, the scheduler manages the cluster to assure a fair share of resources to each job. The third scheduler, named Capacity Scheduler, was developed by Yahoo to guarantee a fair collection of computational resources to a large number of cluster users. To do so, it uses queues with a configurable number of task slots. Resources are shared among queues according to its priority. Free resources from empty queues are temporarily allocated to other queues. While FIFO was the first and most simple scheduler implemented, the FAIR and Capacity Scheduler were created to address the problem of managing multiple users sharing the same resources. Regarding the original schedulers, TAN in 2012 proposed analytical models for FIFO and FAIR schedulers. Based on extensive measurements and source code investigations for a class of heavy-tailed map service time distributions, authors derived the distribution tail of the job processing delay under the 3 schedulers. Analytically, analyzing the delays under different schedulers for MapReduce, the authors discovered an interesting starvation problem with the widely used FAIR scheduler due to its greedy approach to launch reduced tasks. To address this issue, the coupling scheduler was designed and implemented. This scheduler couples the progress of mappers and reducers and jointly optimizes the placements for both of them. Now, TAV in 2011 proposed an improved fair scheduling algorithm which takes into account job characteristics and data locality. This scheduler kills tasks to free slots for new users. It adopts different policies for input, output, and CPU bound jobs based on data locality. Results demonstrate that the improved version decreases both data transfer and execution time of jobs. In the work of Zav in 2012, a new job scheduling based on the FAIR scheduler is presented. The scheduler takes into account job characteristics and similar to the FAIR scheduler, allocates them into queue. The scheduler manages 3 queues, one for large jobs, another one for small jobs, and a third one for priority jobs. The authors claim that compared to the FAIR scheduler, tasks of large jobs can be executed with higher parallelism. Short jobs will not wait, and long jobs can still finish in a reasonable time. And higher priority jobs that come up may be computed as soon as possible. Ibrahim in 2012 developed a scheduling algorithm called Maestro to alleviate the non-local map task execution problem that relies on replica-aware execution of map tasks. To accomplish this, Maestro keeps track of the chunks and replica locations along with the number of other chunks hosted by each node. This way, Maestro can schedule map tasks with low impact on other nodes. Local map task execution by calculating the probabilities of executing all the hosted chunks locally. Other concern regarding schedulers is the heterogeneity of hardware within clusters. A different approach to heterogeneity is presented by Rasuli and Down in 2011, which propose a Hadoop scheduling algorithm that uses system information such as estimated job arrival rates and mean job execution times to make scheduling decisions. Using system information, the algorithm classifies jobs into classes and matches them with available resources. Priority, minimum share required, and fair share of users are also considered when making a scheduling decision. The proposed algorithm is dynamic and updates its decision based on changes in these parameters. Another approach was proposed by you in 2011. A load aware scheduler, known to be LA scheduler, is used in heterogeneous environments with dynamic loading. The scheduler consists of a data collection module which gathers the system level information of the task trackers periodically and a task assignment module which makes scheduling decisions according to the information previously collected. Now let's talk about data flow. What is data flow? The data processing strategy employed by MapReduce consists of two primitive functions, map and reduce. Behind this simple abstraction is a single fixed data flow. A map reduce job is divided into map and reduce tasks and assigned to idle slots of workers according to these two stages. Thus, there are two types of workers, mappers to map tasks and reducers to reduce tasks. In the beginning of the map phase, the input data is loaded into HDFS. To ensure fault tolerance, the input data are partitioned into equal sized blocks and replicated according to the replication factor. Each block will be processed by a mapper, resulting in intermediate outputs, which are locally stored, optionally combined from key value pairs sharing the same key, and stored in local disks of the mappers. The reduce phase starts as soon as there are enough map outputs to start a reduce task. In this moment, the scheduler assigns reduce tasks to workers. The data transfer is performed by each reducer that pulls and shuffles intermediate results using a one-to-one shuffling strategy. Reducers are responsible to read intermediate results and merge them to group all values with the same keys. Subsequently, each reducer applies reduce to intermediate values considering these keys to produce the final output that is stored in HDFS. Now, let's talk briefly about storage and replication. The Hadoop distributed file system is the block storage layer that Hadoop uses to keep its files. HDFS was designed to hold very large datasets reliably using data replication. This allows HDFS to stream large amounts of data to user application in a reasonable time. Its architecture is composed of two main entities, mainly name node and data node, which work in a master-slave fashion. Name node is responsible for keeping the metadata about what and where the files are stored in the file system. Data nodes are responsible for storing the data itself. HDFS works as a single writer, multiple reader file system. When a client opens a file for writing, it is granted a lease for the file and no other client can write to the file until the operation is complete. Additionally, after the file is closed, The bytes written cannot be altered or removed except that new data can be added to the file by reopening file for append. Okay, now let's talk about cloud computing. Although Hadoop is designed to be applied on distributed environments, it was not originally conceived to work using cloud computing concepts. Regarding cloud computing management, in 2011, a person named Kuzuris designed a data management system to enable storage as a service transparently using Hadoop. To do so, the authors require a new file system, ODFS, known to be Optimus Data Manager and Distributed File System, using HDFS as a base. The file system adds RESTful interfaces to expose critical functionalities from Hadoop as services and extends HDFS. These components are used to enrich security, logging, and data analysis features. Components also provide data access compatibility between federated clouds. Using the GFarm file system, Wang in 2013 have proposed G-Hadoop, a MapReduce framework that enables large-scale distributed computing across multiple clusters. It replaces HFDS for the GFarm file system and schedules tasks across multiple nodes of multiple clusters controlled by different organizations. Data transfer between nodes in a cloud computing environment may consume large bandwidth and time. The use of such resources represents an elevation of cost to users. An approach to solve this problem, Hadoop rsync, is presented by Zhang in 2011. Such an approach uses an incremental update derived from the original rsync, which minimizes the data transferred by transmitting only an encoding of the changes to the file instead of the whole file itself. An upload algorithm to update files on Hadoop and a download algorithm to renew files on user side composes Hadoop rsync. The asymmetric scheme is employed because file synchronization in both directions have different characteristics. This approach seems to be suitable for file hosting services using HFDS, which can lower the bandwidth usage and speed up file updates. Resource virtualization is a strong trend industry. The work of Mayo in 2011 proposes a system named EHAD, Elastic Hadoop Auto Deploy, that integrates and shares resources among users on a Hadoop cluster. Virtualization technologies are used to gather physical resources and allocate virtual machines to users. The authors designed a request handler to deploy multi-threaded virtual machines nodes for users. Clusters resources such as computing power, storage, and network composes a resource pool. This pool is allocated for user virtual machines on demand. The created environment automatically deploys the Hadoop framework according to the needs described on user request. This is a similar approach to Hadoop on demand, known to be HOD, which is a system for provisioning and managing independent Hadoop MapReduce and Hadoop distributed file system instances on a shared cluster environment. The main differences relies on the fact that the EHAD approach claims to create, deploy, and destroy Hadoop environments automatically and also on demand. Now let's talk about the DBMS, indexing queries and random access. What are they known to be in Hadoop? Although HDFS shows good performance on scalability, fault tolerance, high throughput, and flexibility to handle unstructured data, it presents drawbacks in some contexts when compared with database management system and other approaches. Leo in 2010 proposed improve Hadoop's performance by means of a complete new indexing manner. Suggest alter existing indexing mechanism as their strategy. Leo in 2010 proposed the use of built-in hierarchical indexing to support complex type queries in HDFS. The method of hierarchical structures is applied to B tree, R tree, and their variants to optimize queries. Several enhancements of index structure with respect to node size, buffer strategy, and query processing were developed using properties of HDFS. In 2012, Dietrich proposed an enhancement of HDFS and Hadoop MapReduce that improves runtimes of several classes of MapReduce objects. The approach named HAIL, known to be Hadoop Aggressive Indexing Library, changes the upload pipeline of HDFS in order to create different clustered indexes on each data block replica. HAIL keeps the existing physical replica of HDFS block in different sorted orders and with different clustered indexes. Hence, for a default replication factor of 3, at least 3 different sort orders and indexes are available. Thus, the likelihood to find a suitable index increases, improving the runtimes for workloads. In the system proposed by Anne in 2010, a global index access mechanism was adopted. The B tree index data is stored in HDFS and distributed across all the nodes. Thus, the index access is parallelized following the MapReduce execution style. This indexing technique is used solution to integrate indexing capability in a non-invasive and DBS independent manner. Indeed, Hadoop B concentrates on query processing, particularly query execution plan. The proposed system boots task performance without changing the Hadoop. Thus, Hadoop B do a hard-coded query processing pipeline explicit and represent it as a DB-style physical query execution plan. The HDFS has been designed originally to support sequential queries. Zoo proposes an approach to enable random queries to the file system. Accessing small data on HDFS may cause unnecessary data transfer. Once the size of the packet may be bigger than the data packet being sent, the approach presents a data transfer policy that supports both sequential and random access. It uses a dynamic method to get the size of data packet. If a random access is requested, the data packet is set to be equal to or less than the required data size. Otherwise, the default data packet size will be used. In 2010, you propose a query optimizer called Hadoop to SQL to work especially when only a subset of the data should be processed. Hadoop to SQL is a hybrid system that seeks to improve Hadoop performance by transforming MapReduce queries to use the indexing, aggregation, and grouping features provided by DBM. The authors proposes two algorithms that generates SQL code from MapReduce queries. One algorithm can extract input set flexibility of Hadoop. The basic idea behind Hadoop DB is to use MapReduce as a communication layer above multiple nodes running single node DBMS instances. Queries are expressed in SQL, translated into MapReduce by extending existing tools, and as much work as possible is pushed into the higher performing single node databases. Okay, what is Hadoop ecosystem? The MapReduce is not suitable for all problem solving large data sets. The four modules that currently composes the Apache Hadoop core are Hadoop Common, HDFS, MapReduce, and Yarn are well suitable for unstructured data. However, when processing common old-fashioned structured data, Hadoop may suffer from performance issues since the framework was not originally developed to process these data. To overcome this problem, several Apache Hadoop related projects have been developed over the past years. For example, PIG, a high level data flow language and execution framework for parallel computation, Mahout, a scalable machine learning and data mining library, and Hive, a data warehouse infrastructure that provides data summarization and ad hoc querying. Corishetti in 2012 proposed the implementation of the dataset structure and operations of union, intersection, and difference in a scheduled manner on top of Hadoop HBase. The work presents optimizations for three set operations and also limitations on implementing these data structure in the Hadoop ecosystem. Zhang and Sturck in 2010 proposed Cloud Batch, a new Hadoop component that enables it to function as a traditional batch job queuing system with enhanced functionality for cluster resource management. The approach allows the cluster management using only Hadoop to discover hybrid computing needs involving both MapReduce and legacy applications. Cloud Batch runs on top of HBase and includes a set of tables used for storing resource management information globally accessible across all nodes to manage metadata for jobs and resources. Energy component. The reduction in cost of hardware enabled corporations to increase the number of data centers and machines. Consequently, energy consumption has become a vital issue regarding costs of data storing and its processing. Several papers discuss the cluster energy management problem generically. Regarding Apache Hadoop clusters, Lee in 2011 proposes an algorithm for maximizing throughput of a rack of machines running a map reduced workload subject to a total power budget. The main idea is to optimize the trade off between job completion time and power consumed. The novelty in the approach relies on the accounting for thermally induced variations in machine power consumption. The algorithm minimizes job completion time for any given power budget. Green Hadoop, proposed by Goiri in 2012, is an Apache Hadoop variant for data centers powered by photovoltaic solar arrays and electrical grid as a backup. The objective is to investigate how to manage the computational workload to match the green energy supply in small medium data centers running data processing frameworks. However, scheduling the energy consumption of map reduced jobs is challenging because they do not specify the number of servers to use, their runtimes, or their energy needs. Moreover, power managing servers should guarantee that the data to be accessed by jobs remain available. Green Hadoop seeks to maximize the green energy consumption of the map reduced workload or equivalently to minimize its brown energy consumption. Green Hadoop predicts the amount of solar energy that is likely to be available in the future using historical data and weather forecasts. By using these predictions, it may then decide to delay some jobs to wait for available green energy, but always within their time bounds. If brown energy must be used to avoid point violations, it schedules the jobs at times when brown energy is cheaper, while also managing the cost of peak brown power consumption. Okay, now let's talk about general purpose computing on graphic processing units, which is known to be GPGPU. GPGPU is a technique to use commodity GPUs to perform general purpose computing in applications traditionally handled by CPUs. CUDA, and OpenCL are examples of integrated development environments that may be used to such purposes. Shirata in 2010 presents a hybrid map task scheduling technique for GPU based heterogeneous computer clusters. The developed job scheduler assigns the map task onto CPU cores and GPU devices in order to minimize the overall map reduced job execution time. The scheduler uses profiles collected from dynamic monitoring of map task behavior to decide where to schedule a task. Jobs containing tasks that have data parallelism may be suitable for GPU execution, while tasks containing many branches or synchronizations are not recommended to be executed using this approach. The model uses Hadoop pipes, a C++ interface to Hadoop MapReduce. Hadoop pipes uses sockets as the channel over which the task tracker communicates with the processing running the C++ based map and reduce functions. Its use is justified because other native methods such as Hadoop streaming and Java native interface, known to be JNDI, may introduce significant overhead, representing loss of performance. Zinn and Lee in 2012 have successfully demonstrated that the use of OpenCL in commodity Hadoop clusters may outperform regular clusters significantly. Their approach concerns to both data and compute intensive applications. Grossman 2013 also integrated OpenCL into Hadoop to enable the use of heterogeneous processes, such as the CPU and GPU combination. This approach can achieve nearly 3 into overall speed up for some specific Hadoop MapReduce applications. Another approach by Fang in 2011 is named Mars, a MapReduce runtime system accelerated with GPUs to improve Hadoop performance. Mars run on NVIDIA's GPUs, AMD GPUs as well as multi-core CPUs. Mars was integrated into Hadoop being called Mars Hadoop. Now, let's finally wind up this topic by talking about the importance of the data security and cryptography in Hadoop. In the cloud computing era, data security, privacy, and integrity became important features to be supported by frameworks and service providers. In Apache Hadoop, data is stored according to user accounts. This mechanism may not be secure enough when dealing with data spread across multiple data centers and cloud providers. Some studies addresses these problems, presenting solutions to enhance both Hadoop data security and confidentiality. We in 2009 designed a model that enhances the basic MapReduce framework with a set of security components. In open systems, MapReduce faces a data processing service integrity problem since service providers may come from different administration domains that are not always trustworthy. The approach is meant to provide a service integrity assurance framework for MapReduce, replicating some tasks and assigning them to different mappers reducers. This is achieved by using a decentralized replication based integrity verification scheme for running MapReduce in open systems. Another approach proposed by Lin in 2012 addresses the data confidentiality issue in Hadoop by enhancing HDFS. Two hybrid encryption schemes were implemented and integrated into HDFS to achieve data confidentiality. The HDFS RSA, which uses the RSA encryption, and AES and the HDFS pairing, which uses a pairing based encryption scheme, and AES. As expected, both schemes introduce overhead on reading and writing operations. The biggest overhead is on writing because the encrypting process is accomplished in two parts. Reading operations also have an overhead, although it is much lower and acceptable than the writing overhead. Concerning problems with the data integrity in cloud, Nguyen in 2010 proposes a model called OPERA, Open Reputation Model, that employs reputation based trust management to improve Hadoop computational efficiency. In general, the existing methods rely on a single value reputation to capture the differences between service providers in terms of properties such as performance or availability. Thank you for watching my video, and my special thanks to my professor Dr. Yang Lee for the guidance for making this video.